Welcome, everyone. Thanks for joining us. You are tuned into the Boise State First Friday Astronomy event. Uh, for those of you who have never attended before, welcome. This is the monthly lecture series that Boise State Physics hosts. We bring in a space scientist or a space policy person to come in and talk about their work. So usually we have a space scientist or an astronomer of some type, but very often we've brought in space policy folks, people who work in Washington with Congress to develop space policy. We've brought in science journalists. So it's kind of a wide range of folks who come in and talk with us. They occur, as you might expect, on the first Friday of every month. So this is the first Friday of March. And so we're having a talk this evening. Our next scheduled First Friday Astronomy talk will be on February 2nd. And we'll have Dr. Ami Choi, who will talk to us about her astronomical research. That'll be really interesting. We're in for a real treat tonight. In addition to these First Friday astronomy events, we've begun hosting Third Thursday virtual planetarium shows. And so those take place, as you might guess, on the third Thursday of every month. And so the very next one of those is scheduled to take place on March 18th. Those are a little smaller and less formal. We invite folks into the Zoom room, basically, and we just talk about how to do stargazing. We talk about a little space science. It's kind of an open forum for asking questions about astronomy and space science. Those are also virtual as well. And so those take place on the third Thursday, also at 7:30. If you would be interested in attending one of the third Thursday virtual planetarium shows, I've posted a link in the chat on the YouTube live stream. But the URL to sign up for those is boi.st/third Thursday. So that's boi.st/third Thursday. We ask that you sign up, register just because they take place in these Zoom rooms. Okay, excellent. Well, we are in for a real treat tonight, as I said. Our guest speaker this evening is Professor Lindy Elkins-Tanton. She's someone of many parts, and I think she's one of the most exciting folks in planetary science nowadays. Her research involves theory, observation, and experiments having to do with terrestrial planet formation, magma oceans, which is, I think, one of my favorite topics in planetary science, and planetary evolution after planet formation. She has done lots and lots of really great things, but one of the most exciting things she's done, and I think what we're going to hear about tonight, is her work on the NASA mission Psyche, which is going to an asteroid. And with that, I am going to stop talking and let her tell you about herself. So, Lindy, why don't you go ahead and take it away?
Fantastic. Thank you so much, Brian. And thanks everybody for coming. I'm really excited to share
You might
tonight.
be muted. Your volume just... Oh, no, I'm sorry. Go ahead. Please go ahead.
Okay, everything okay? Is it all right? Yeah? Okay, cool. I'm very excited tonight to share with you about the mission Psyche. So let me share my screen because, of course, we have an exciting PowerPoint, which is how these things so often go. All right, I'm going to talk about the NASA Psyche Mission, which is a journey to a metallic world. And this is an artist's conception of what Psyche might look like, done by our great artist friend, Peter Rubin. So we have, as humans, we've visited rocky worlds. Here's the moon, the limb of the moon that we can't see from the Earth. That's the Orientale crater. It's a beautiful crater on the moon. Rocky worlds like Mars, and icy ones like the moon Europa right here, a possible place to go look for habitability and maybe life, and gassy places like Jupiter. No, we have never before visited a world that we think is made largely of metal, a metallic world. It's a new kind of exploration. And so I'm going to tell you tonight a little bit about the process of how the mission came about, how you create a NASA mission, and where we are in it right now, and also ways that you can be involved, which is always a part of the point, I think. So it started in 2011 with this paper. And this paper with the ultra compelling title, Chondrites as Samples of Differentiated Planetesimals, that I wrote along with my friend Ben Weiss and my friend Maria Zuber. And if you're not in the field, you know, this would seem like any old paper. And if you happen to be a meteoriticist, someone who studies meteorites, this was a bit incendiary. We were suggesting with this paper that the most primitive meteorites, called chondrites, meteorites that fall to Earth today, but are the remnants of the very beginning of the solar system, remnants that are like the raw remnants, like they never melted, they really weren't heated very much, they weren't affected by very much fluid, they're supposed to be the most primitive stuff ever. And we're suggesting that they came from parent bodies that were differentiated, meaning they completely melted, and the metal had drained to the middle and made a metal core surrounded by a rocky exterior, the same structure that the Earth has and the other rocky planets. And so we are suggesting that this very primitive material came from the outside of a differentiated body. And it made a lot of people really upset, which is sometimes kind of fun in science. And we had lots of great conversations, and it does seem like this must be true in some cases. But this paper had a quite unexpected result, which was back there in 2011, I got an email from Jet Propulsion Laboratory from two scientists there, Daniel Wenkert and Bruce Bills, saying, we really thought this paper was interesting and we would like to talk about proposing a NASA mission to test your hypothesis. And so it wasn't that I had set out to say, I know about this asteroid Psyche, we have to go visit it, it's going to change our conception of this planet's planetary system. It was that I'd written this paper and these people said, you know what, this might actually be a testable hypothesis other than just meteorites. And so this is just to show you what creating a NASA mission is like. We started talking in 2011, and through 2011, 2012, 2013, trying to convince Jet Propulsion Laboratory that they wanted to be our NASA center. In the beginning, we also had to decide where we were going to go because it wasn't obvious that the answer was Psyche. And in the end, we decided that was the #1 best place to go in our solar system to try to understand the differentiation, the core formation processes in planetesimals, these very early small bodies in the solar system. We had to select a partner, which we did, wrong way, which we did back at the end of 2013. We chose Maxar Technologies, and then we had to write our proposal, 250 pages, and submit it. And at that point, we had probably 50, 60 people on the team. And we waited. There were 28 proposals that went in, and NASA selected 5 to go on to step 2. Now we were quite surprised because you usually, so now we're 5 years in to the work that we've been doing, 4 years in. And normally you're not selected the first time around. So normally you get better and better. You kind of zone refine and make your proposal better as you compete through multiple rounds of these competitions, but they only come every 3 or 4 years. And so it's a multiple decades of efforts to try to get a mission selected. And of course, most are not selected in the end. So we were very lucky. We got to step 2 in 2015. And then we had another proposal to write that was 1,000 pages long. And by the end of 2016, we had 140 people on the team. And submitted our final proposal. And then in early 2017, I got a call from NASA early one morning saying we'd been selected for flight. So we went 5 years from conception to selection, which is about as fast as you could ever hope to go. It was a kind of a dream to get to that point. And I'll tell you where we are more in a moment, but I wanted to kind of give you that run up so you know a little bit about how the thought process goes and why it is that we chose this object. So this is the theory. The theory is that within possibly even just as little as tens of thousands of years after the very first solids in the solar system, which remember is 4.568 billion years ago. Remember that number? I always joke that if you don't remember that number in my classes, I fail you, 4.568 billion years ago. And so in a virtual eye blink, these bodies that are called planetesimals had already been formed from the dust and gas. And these are bodies that are tens to hundreds of kilometers in radius. And you can see there on the left that I'm showing one that's just all layers of brown, like it's a little warmed up, it's like an onion shell, but the one underneath with the red has melted. And the metal has flowed to the middle and made a metal core, and it's surrounded by a rocky exterior. They collide together and eventually grow into bodies called embryos and finally into planets. So that's, I'm skipping over all the details, obviously, but that's kind of the current theory for how rocky planets are born. And we wanted to go right back to that first step with planetesimals and see if we could learn about the very first metal cores that ever formed in the solar system. So that's where we're going with this. This is our hypothesis for Psyche. And this was another thing done by Peter Rubin. Before I walk you through it, I just have to say that we realized at a certain point after we've been working on this for several years, and you've seen the timeline, so you can imagine where we were, that we scientists had in our heads a kind of a film strip of how we think Psyche was formed that was not shared by the brains of other people who were not planetary scientists. And we realized that things like the instruments we wanted to fly on the spacecraft or the kind of data we wanted to gather was all motivated by this film strip we had of our hypothesis of what Psyche was. And we had to share that film strip with the rest of the team so that everyone would understand why we were choosing what we were choosing. And so we got Peter and I used to Zoom together on Saturdays or Sundays for like a year or 2 years to get all this work done, get it really scientifically motivated. So if you look up at number 1 on the top left, you see a planetesimal that's molten on the inside. The metal has sunk to the middle and it's all shown as orange, as liquid iron nickel metal, which is what we think it is with the rock on the outside. Now, how do you get a body to be mostly metal? Well, we think the likeliest thing is that it had several strikes by other objects, as you see in the center on the top, pow, that knock off the rock and leave the metal more exposed. Here we're just showing one of those impacts, but we actually think that it had to have between 4 and maybe even 11 destructive impacts to strip off most of the rock and leave it metal as it is. And so that metal interior then reforms in number 3 and number 4, it's creating a magnetic field because it's convecting, circulating liquid metal, making a magnetic field the same way that the Earth has its magnetic field. It's gradually freezing. You can see the crust of it freezing. And then finally in number 8, it gets knocked over on its side, presumably another impact. And in fact, Psyche's is over on its side in terms of a spin axis out there in the solar system. And that makes it interesting for the mission. That's a mission planning issue. So that's what we call our fiducial hypothesis. That's where we start from in thinking about how Psyche was formed. And so now you can understand our cover art. So here is this by the way, this is one of the things that is quite mind-blowing to us ordinary scientists when we go into writing NASA missions. There's so much money at stake and so many years of people's careers. So many people. Right now on our team, we have 800 people working on this team. There's a lot of money behind it. And that includes needing things like some professional cover art. So things that we don't normally get to do when we're writing proposals to NSF. So here's the cover of our very first proposal, the step 1 proposal. And you can see now what we're trying to show. We're trying to show the moment of one of those impacts that's going to strip the rock off of that planetesimal and make its metal core visible. So that's the moment of impact. And then this is our step 2 proposal, maybe 30 seconds later. Actually a year later, but in real time, but in the time of the story, maybe 30 seconds later, and there's that impactor screaming off to the bottom left, and you can see what the artist is just trying to show, that the boiling hot liquid iron nickel metal core is being revealed from underneath the streaming off pieces of rock being pulled off it. And here is one of the many points in this talk where I'm going to remind you that all of this is definitely scientifically motivated with the best information we have, but it's almost certainly wrong, because every time we go to space, we're completely surprised and we learn things that we never expected. And I'm here to tell you, we do not really know what Psyche is. This is just our simplest guess, and really we're probably wrong. And so stay tuned, and then you can say, she said, and she was wrong when the time comes. So back on March 17th of 1852, Annibale di Gasparis discovered Psyche from the observatory in Naples, Italy. And so March 17th, some people think it is for some other purpose, but March 17th is actually Psyche Discovery Day. And so I hope you'll all be, celebrating Psyche Discovery Day with us in a couple of weeks. It's called asteroid 16 Psyche, as I know some of you know, because it was the 16th asteroid ever discovered. And there's such a great story about the early people who discovered the asteroids, which I am not going to tell you right now, but if you would like me to talk about it later in the question section, I'd be happy to. So here's our hero. He found this asteroid, although at the time he had no idea that it was made mostly of metal. So here's a very, very important point. I've been showing you all of these cartoons and images of our ideas about Psyche, but this is actually what Psyche looks like from the Earth. We do not know what Psyche looks like. We have no high definition space-based photographs of any asteroid that we think is mostly made of metal. This is a picture of Psyche that was taken in our backyard here in Phoenix with a very nice telescope from our astronomer friends, Patrick Young and Karen Neerman. They brought it over and we looked at it. This week, we got an amazing thing that I can't show you, but I can describe it for you. Mars Express, the Mars orbiter, someone who's on the Psyche team is the principal investigator for the high resolution camera on the Mars Express orbiter. And they took a picture of Psyche from Mars this week and showed it to us. Mars is much closer to Psyche than Earth is, although actually not at the moment. They're not very close in their orbits. And Psyche looks just like this from Mars. So it's relatively small and far away, and we really know it as more or less a point of light. If we were to bring it to Earth, this is how big it is. It more than bridges the distance between Los Angeles and San Diego. It's about the size of Massachusetts. It's a little smaller than Switzerland. It's about 230 kilometers in diameter. And so as asteroids go, it's quite large. And because it's so dense, it's about 1% of the mass of the asteroid belt. So pretty good size asteroid. And these are the best images that we have of Psyche. These are taken from the European Southern Observatory. And they actually are able to show Psyche as it spins. They could see that its shape seemed to change. And so by taking pictures as it's spinning and comparing the light curves, and they could actually make a shape model. And so they and 4 or 5 other groups have done this. So we think we have some idea of what Psyche's shape is. But this is about as good as the fidelity is, and the models don't actually really agree with each other, and so there is some difference. So we're going to be surprised when we get there. That's the thing to know. So the fundamental shape model of Psyche is known sufficiently well to have a volume that agrees within about 10% for the most recent 3 estimates. What I just showed you was from Vik and Koski, that bottom one. At their 1 sigma errors for you scientists, it's about a 30% difference. And so we don't really know its volume. And because people have measured its mass from how it interacts with other bodies, but that has errors too. And so if you have its mass and you have its volume, you can use those to get its density. And from its density, that's one of the main ways we infer that it's largely made of metal, but there are errors, right? There are errors there. And so this is what we know about Psyche from Earth right now. We think that its bulk density is between 3,700 and 4,200 kilograms per meter cubed. And for those of you who don't have like planetary materials densities inserted into your brain, I will just tell you that is denser than solid rock that we would expect, and it's less dense than solid metal. So it can't be 100% iron nickel metal unless it's metal with lots of pore space and fractures, and it's basically a rubble pile, which is possible. But it also can't be just rock unless it's really dense, unusual rock. Rock mixed with metal is maybe the best thing that we would guess. So we guess that it's probably between 25 and 60% metal. It could be as much as 100% metal if it's a rubble pile. But that's just the information we have now with all the errors that we have now. Now, the other thing that people do to look at Psyche is they look at the reflected light off of Psyche. They look at its spectra. And we've learned so much about what spectra tell us about the composition of the material that's reflecting the light. And here's something that might seem to you to be unbelievably specific. The part of Psyche that isn't metal, the part that's rock, seems to have very little iron oxide in it. Most minerals on Earth have quite a lot of iron oxide in them, and we think the rocks on Psyche do not, and that is unusual and weird. And so why am I telling you this? It might seem like too much of a detail for a talk like this, but here's why. None of our hypotheses for how Psyche could be formed really satisfactorily explains all of the observations we even have so far. And so these observations might be wrong, or Psyche might be something even weirder than we even imagined. And so I think that's kind of fun. So for those of you who are mineralogy people, the people think that the other thing might be low calcium pyroxene, a particular mineral. And then the question becomes, how do you make something that's made of metal and pyroxene? There's not really a great way to do that. And so we don't know. Mysteries is the point. Mysteries. So here's a graphic where I'm going to show you what our best ideas are about Psyche. So, and then I'm going to get into the technical parts of the mission in the sense of what instruments are we flying and what does the spacecraft look like and how is the trajectory going to go through space. So rock and metal core, so a melted differentiated planetesimal like we were talking about in the beginning on the left, and here the rock is colored green and the metal in the middle is like silver colored. When it freezes, it turns out that theory says that the rock near the core should have almost no iron oxide in it. So that's hopeful for us, right? Because we think our rock has very little iron oxide and that it has metal as well. And so there are two ways that you could make a Psyche out of this. You have to have impacts that strip the outer higher iron rock away and leave pieces of the metal core with a low iron rock from near the metal core. So that's our fiducial hypothesis, really. That's like the Peter Rubin POW scenario. You know, or maybe the rock and the metal is more intimately mixed and we got sort of the core mantle boundary of a much bigger object, which is kind of amazing. Like maybe there's actually reasons to think this could have been something that was more Moon or Mars sized that got fragmented in a giant impact. That would be pretty exciting. The other hypothesis, and this is exciting for people who are like nerding out right in planetary science, is that this is primitive material. Remember, I used that word chondritic in the beginning about that paper that I wrote with Ben and Maria. Material that never melted, that's very, very primitive. Most chondritic meteorites that are very primitive do not match Psyche in any way. But there's one particular kind that does, or maybe two, that are high metal, very low iron oxide. It's possible that Psyche is one of those. Or maybe it's none of these. Maybe it's something else entirely. And any of these could have been made into rubble piles too. So what I'm trying to tell you here is that we have some data that points in a particular direction. Pretty sure it's got to have a lot of metal in it. Other than that, there isn't a really compelling story that seems really solid for exactly how you'd make a body that's like Psyche. So not only is it a kind of body that humans have never investigated, we're really expecting it to surprise us. We're really expecting it not to be what we expect. And I love this. There's a stage in the NASA proposal process where you're supposed to put in a table for all the data that you're going to gather, and then a column that says the percentage improvement that you're going to have over existing data. And because there have been no visitors to metallic asteroids, no robotic visitors, basically it was an infinite improvement of data, of every kind of data, because there is no data. And so that's especially fun. All right, so here's one idea. So this is a kind of meteorite, the vermilion pyroxene palisite could be the core mantle boundary kind of thing that we're talking about with Psyche. The silvery parts are all iron, nickel, metal, and they have the beautiful crystal pattern that's called a Widmanstätten pattern of that almost looks like plaid intergrown crystals. And then you see little pieces of rock, silicate rock in here, and one of them shines kind of gold, and that's a pyroxene mineral crystal. And so this is actually a candidate for what Psyche might be. Psyche, unfortunately, will not be sliced and polished the way this one is. And so it's probably not going to be all shiny and gorgeous like this, but this is a possible thing that Psyche could be made of. And here's another one. This is a chondrite. This is from an unmelted rock. Straight from the very beginnings of our solar system. It's shiny on the right-hand edge because light is reflecting off many, many tiny metal pieces. It's called an enstatite chondrite, and it's probably the material that Earth was made of. And this is not a terrible match for the spectra of Psyche. It's within the realm of possibility for both density and spectra. So this could be, Psyche could be the biggest remaining piece of Earth's material that is not in Earth. So that's kind of cool. And then here's the last opportunity, the last possibility. There's a really weird class of meteorites called the CB chondrites. And if you look especially on the one on the top left that's called Gujba, you see what look like, and probably really are, frozen droplets of metal. It looks like that iron nickel metal was liquid and then it froze, almost like iron nickel metal bubbles. And that's actually what we think that is. It could be like the spray from a giant impact into its parent body possibly. And in between on these CB chondrites is silicate rock that is very low in iron oxide. Now these are very rare meteorites and they're very strange. And if Psyche was their parent body, that would be amazing. So we don't have any simple common analogs for Psyche right now. Everything that's lining up to match the data we have is weird. So I love that. All right, so our first objective, well, I should have just said, oh, where did that go? I'm confusing myself with my own talk. Let me just address it. Oh, here it is. Okay, sorry. So up at the top, I meant to really read the title of the slide. So the very first science objective we have for this mission, objective A, is determine whether Psyche is a core or if it's unmelted material or some other kind of material. And so our first guess is that it's a core. And so this is our very first goal of the mission, is to determine whether it's a core or if it's something else. So what is its provenance? Now, the second objective we have, objective B, is to determine the relative ages of surface regions. And we'll do that by looking at how many craters there are on them. And I suspect that a number of you are very familiar with this idea that the longer a planetary surface has sat out there in space, the more craters as it accumulates from material falling in and making craters in it. And young surfaces, like the surfaces on Earth, are young because our weathering and our plate tectonics is constantly resurfacing them. It gets rid of the impact craters and you don't see them anymore. So those are young surfaces. And so we're going to look at the different surface regions of Psyche and compare their ages. I'm going to skip objectives C and D. They're very technical ones, but I want to talk about objective E, which is to characterize Psyche's morphology, the shape of a body that's made mostly of metal. Now, right here is an impact into meteoritic metal with my thumb for scale, so it's a small impact, that was made in the Ames vertical gun, where they can shoot projectiles at planetary type velocities and see what kind of impact craters they make. And if you've looked up at the moon, you're kind of used to seeing impact craters that are round and maybe they have a little rim around them, but they're not really shaped like this. This is weird. Notice how down at the southwest, like at the 7 o'clock side of this crater, there's an overhanging lip of ejecta. And so that's one thing that happens in relatively small metal impacts, is that the ejecta flaps freeze before they fall down again. And so that's one weird thing we might see on Psyche, is some frozen ejecta pieces that might still be standing up for smallish craters. And then you also see things on here that are cracks that are radial inside the crater, and then that are azimuthal inside the crater, and then ones that are radial outside the crater. So big impacts on Psyche really might look nothing like craters on any other kind of bodies we've ever seen. And so that's going to be a large part of the fun, is figuring out what the surface features are, because we really have no idea what it's going to look like. And so we collected all the little bits that got shot off of the impacts at the Ames gun. This is work done mostly by Simone Marchi at Southwest Research Center and Carol Polanski from JPL. And we collected these little pieces. Some of these impacts, by the way, were done at liquid nitrogen temperatures to see if the metal behaved differently, which it does, and its strength is different. And we think right now that this might be the only way that we can make a metal regolith, like a soil or a sand made of metal on a metal body. Solar wind and impacts on rocks actually break them down into grains and make them into a regolith or like a sand. That doesn't happen with metal that we've been able to detect so far. There's a graduate student at Arizona State University, John Kristoff, who's doing his thesis on this. What does the solar wind do to metal? Would we expect it to break into pieces? And so far, the answer seems to be no. This might be the only way to make metal. And it's very sharp and angular, so it would be a pretty strange kind of surface. All right, so now back to the story of the mission. So this is 2011 through 2016, which I already talked about in that other slide. And here's the rest of the mission. So after selection in 2017, which you can see on the bottom left, we went right into phase B, which is the formulation phase. And that was 2017, 2018, the beginning of 2019, just making sure we really knew what we were going to build. And it actually takes hundreds of people working for years. That's how complicated these things are when you want them to work in space forever without needing a repair. We went through two big reviews, the preliminary design review, PDR, and the critical design review, CDR. CDR was last year, shortly after COVID shut down the country. And NASA had never done a virtual CDR before. And so we had to do our CDR and also do it in a new way that had never been done before. CDR is very intense. It is normally 8 hours a day of presentations for 5 days straight, in front of a paid professional review panel and 100 or 150 additional people. So it's super intense, and if you pass, you get to keep on building your spacecraft. And so we did pass, and it was a big deal. And we're now in 2021, we're about to go into, in just a couple weeks, we're going to enter the final phase, assembly, test, and launch operations, which is phase D, and it's called ATLO. And that is, as you can imagine, unbelievably intense. The big spacecraft is going to be shipped down from Maxar to Jet Propulsion Laboratory. We're going to start integrating the science instruments onto it, the rest of the power system, the computer brain of the system, uploading the software, testing everything every different way, and eventually shipping it to the Cape so that it can be launched in August of 2022. And so after launch, we'll do a Mars flyby, which I'll show you in a moment, and we'll cruise out to Psyche over 3.4 years and arrive right in the beginning of 2026. And so you can see that suddenly going from a person, kind of a career where you're writing papers every few months and working with students and writing proposals that hopefully fund you for a year to 3 years at a time, suddenly 15 years is taken up on this, and this is a minimum amount for most missions. It's a big commitment. So, the mission is led out of Arizona State University, where I am, and our major partners are Jet Propulsion Laboratory and Maxar. And then people who are building science instruments for us are Johns Hopkins Applied Physics Lab, Malin Space Science Systems, and the Danish Technical University. And although this is an artist's interpretation, it is actually quite exactly accurate to the spacecraft that we're building, because we now know absolutely everything about it, and big parts of it have already been built, which is really amazing to see the hardware coming along after all this. So we're going to fly multispectral imagers, that's on the left. So these are cameras that have filter wheels that allow us to measure specific wavelengths of light, and they actually give us some compositional information as well as pictures of the body. And then because we can take pictures from different angles, we can build a topographic map of the surface of the body. So we'll get the topography that way. And because on this mission, we feel very strongly that the purpose of space exploration beyond fundamental science is to inspire and involve every human on Earth. We will be putting those images out on the web within 30 minutes of our receipt. Perseverance rover is doing a great job at putting images out on the web and making them available, and we'll be attempting to beat their speed record. Some missions withhold all their data, including their images, for some time so that they can be vetted and make sure there are no anomalies or anything confusing, and the team can look at them first, but we really think everyone should be able to scratch their heads at the same time. So the second instruments that we're flying are the magnetometers that are made by Danish Technical University, and we're going to fly 2 of them. I'll show you in the next picture. And then finally, the gamma ray and neutron spectrometer on the right, made by Applied Physics Lab. This is an amazing instrument. I think we all have some sense. Magnetometers measure the magnetic field, imagers take pictures like cameras that we have, like that all makes kind of sense to us in our normal lives. But the gamma ray and neutron spectrometer measures the composition of the surface of Psyche, atom by atom. It doesn't measure mineral types or crystal forms. It actually measures the individual atoms. And here's how it does that. This is something I love so much. I love talking about it because it's so crazy. So many of you, I'm sure, know about, and maybe some of you don't, these things called galactic cosmic rays. And these are very high energy bits of radiation that zip around our solar system all the time, and they come largely from the centers of galaxies, and maybe also from stellar collapse and explosion. It's not totally clear that we know everything about them yet. They range over a very wide span of energies, and some of them are extremely energetic. They're a big problem for astronauts and for spacecraft, and we are shielded from some of them by our magnetic field and atmosphere. But Psyche doesn't have an atmosphere, and so the cosmic rays strike the surface of Psyche, and they energize individual atoms in Psyche, and those atoms, when they relax again, give off gamma rays and neutrons. And the gamma rays that are given off by those atoms have a characteristic energy depending on what kind of atom it was. So we're going to be orbiting around Psyche with an amazing crystal that when those gamma rays strike the crystal measures them. And we will be able to count the energies of the gamma rays that come off the surface of Psyche after being impacted by cosmic rays. And we will then know what atoms make up the surface of the planet, of the body. It's quite amazing technology, I think. It's just kind of blows my mind that we can do this. So here's our spacecraft. It's quite large. That's some sort of human for scale. It's basically 3 meters cube, but it's not quite a cube. And if you look up at the top, there's quite an amazing superstructure. This is just 2 views of the same spacecraft. So up on the top left, you can see the gamma ray spectrometer and the neutron spectrometer is being held away from any kind of gamma rays and neutrons that the spacecraft itself is giving off, because we don't want to measure the composition of our spacecraft. We want to get the stuff only from Psyche. And then on the right, you can see the magnetometers are up also on a boom being held away from the spacecraft in what we call a gradiometer configuration. So we can measure the difference of the field that's measured by the outermost magnetometer and the one that's closer to the spacecraft. And that allows us to subtract away the magnetic field that the spacecraft itself produces. And that way measure only what we hope to be a lovely magnetic field that Psyche still has. We don't know if it has one. We really hope it does. You can see the cameras poking out the back, and the word cameras is right above that strange person's head. And then you can see the high band, the X-band high gain antenna that we'll be doing our communications with Earth with. And then on the left, down near the bottom, it says DSOC, DSOC. That's the Deep Space Optical Comm. This is a technology test that NASA has asked us to fly. It is completely separable from our science mission. It's really a separate purpose of the mission. And we're going to test it as we're going out past Mars. It is a laser communication system. Turns out you can send a lot more information with lasers than you can with radio waves. And so we all think that the future of space communications with Mars, people joke it's like how we're going to stream Netflix to Mars, is by using laser communications. And so we're testing this laser communications device. There's going to be a transmitter out of an observatory in California that's going to send laser pulses up to Psyche. The DSOC is going to detect them, and it's going to send laser pulses back to a different receiver in California. And these receivers are made of an array of superconducting nanowires. So these are very, very tiny wires. I love the phrase. I say it as often as I can, superconducting nanowires. Tiny, tiny wires in an array that are held near absolute zero so that they're in a superconducting state. And when a single photon from the Psyche DSOC laser strikes them, it warms them up just enough that they no longer superconduct. Suddenly there's high resistance, and then the device immediately cools them back down again. And that way the device can count individual photons coming in from Psyche. So there's some crazy tech for you. Now, you see this giant, giant spacecraft, and you see these, all of our 3 science instruments are basically hanging off the outside. So what is inside this thing? Not a lot, actually. We've got huge tanks of xenon that is the propellant for our ion thrusters. So we have these Hall effect ion thrusters that actually propel the spacecraft using xenon that is ionized and sent through a little potential field. And a lot of the rest of the inside of the spacecraft is empty. Why would we do that? It seems like a waste. Well, it's not. It's actually saving taxpayer dollars. This is the smallest, more or less off-the-shelf satellite that Maxar builds. And so because they built it so many times, they know exactly how to build it, they could give us a firm fixed price to build this item. And by doing that, we saved a huge amount of money. So we bought a bigger house than we needed, but it ended up costing a lot less money. So that's kind of the story of the spacecraft. Now we have gorgeous solar panels. This is a solar electric mission. We need the electricity to run those ion thrusters. And when they're unfolded, in the previous picture, they would have been folded up like accordions right against the side so it can fit into the rocket fairing. And when it's unfolded, it's almost 25 meters long. So it's about the size of a singles tennis court when those are unfolded. So we're going to launch on a SpaceX Falcon Heavy, which I am ridiculously excited about, actually. And they are going to try to re-land the boosters from our launch. And I had a super exciting moment today when I saw the first mock-up of what the NASA logo and the Psyche logo are going to look like painted on the rocket, which for some reason it feels to me like choosing the color of your new car. Like it's one of those just pure fun moments, really exciting. So we're going to launch from Earth in August of 2022. We've got 90 days of checkout. The blue dots are when the deep space optical comm is going to be practicing. We'll do a Mars flyby in May of 2023, and it'll give us a gravity assist, and then we will zoom out to Psyche. We'll arrive in January of 2026. This is an orbiter only. This is not a lander, and it's not a sample return. So we're going to orbit for 21 months while Psyche goes about that far around the sun, and we'll end orbit ops in October of 2027. And we'll be getting data all that time. So when we get, oh yeah, sorry, I skipped a slide. I took a slide out. Now I just want to tell you very briefly about some of our student collaboration programs. One of them is called Psyche Inspired. This is a kind of birthed by the idea that a number of us had that all the things we do, art, theater, policy, science, engineering, are all ways that we humans try to apprehend our world. And this idea that very different kinds of people do them, or that they're really, really different disciplines, I think is false. And so I'm always trying to find ways that we can bring people of different disciplines together to think about the same thing. So every year we take applications from students in the United States at 2 or 4 year colleges. Those are the requirements. Has to be you can be a foreign student, but you have to be at a US institution, 2 or 4 years, any major, an application to do art with us. And we pick 16 people per year, and they get funded to create 4 original works of art during the year. So we create new art every single year. We're in is it our 3rd year or our 4th year right now? I'm not really certain. But it is this very, very rich way to think about the mission and what we're doing, and think about space and humans' experience in space. The team gets very involved. They love meeting and talking with these students, and we do virtual galleries at the end of the year, and we publish books. And we have everything also on our website to share with you. We are very proud of the extent of our student collaborations. We actually have 4 student collaboration projects or programs, and that one I just told you about is just one of them. What this slide is to show how many students we've already had work on the mission, because we really wanted to make our student collaborations more than 30 students get together and build an instrument that flies on the mission. We really wanted people to be involved over many ranges of kinds of involvement. So the horizontal axis here is time. So starting with mission selection of 2017, in January, we actually had our first cohort of students. These are mostly capstone students who do special interdisciplinary capstones with us based on real problems that the mission is trying to solve. That's another of our programs, but all 4 programs are wrapped up in here. Then on the vertical axis are students. Every single little tiny hair-like horizontal line is 1 student. So most students stay for 2 semesters, but you can see some, the lines go all the way across. And so as of the end of 2020, we've had over 800 undergraduates work with the mission in one way or another. And we've had some more in the beginning of 2021 that aren't even added onto this yet. And so that is my short story of Psyche today. I want to invite you to come to psyche.asu.edu, where we have so much information about the mission. The mission and I are both on Twitter, and the mission is on it's on Instagram, and it's also on Facebook. And so we try to share everything we can about what's going on, and we share the art that the students make, and we share any opportunities we have. And on Twitter, I and a bunch of other mission principal investigators, which is the name of a mission leader, have started a hashtag, which is hashtag PI_daily, PI daily, just to try to give a sense of what we're actually doing day to day and what happens on a mission and all the things that go into creating a mission. And so if you're interested in this kind of thing, you can follow the hashtag PI daily. That is it for tonight. And so I'm going to stop my share, and would love to answer any questions that people have.
Yeah, folks. And so as with previous First Friday Astronomy, I'm going to ask you to put your question in the chat window on YouTube. So let me see. I'll start with the students in the room. Do any of the students in the Zoom room here have any questions?
Brian, do you want us to go ahead and speak, or should we?
Yeah, you can go ahead. Yeah, for sure. Go ahead.
First of all, Dr. Elkins-Tanton, thank you very much. This is fascinating, and it's going to be an amazing mission to watch. I wanted to ask a little bit on kind of asteroid mining. I know that that had been in the news for a while, and then I think it
Yeah.
was ESI and Planetary Resources both kind of faded off the stage. But where do you see this going in terms of stimulating interest, or is there
Yeah.
even sort of business involved or corporate interest involved kind of right now with this mission or in watching where it goes?
Yeah, that's
Thank
a
you.
really great question. There's absolutely not any business involvement of the mission. This is absolutely a pure science mission run out of NASA. But I'm certain that everybody around the world who's interested in asteroid mining in the future is going to be watching for results, just like they do from the other great asteroid missions that are out there, Hayabusa and OSIRIS-REx, and these fantastic things that are happening. Psyche itself is really too far away. It's way out past Mars. It's in the outer main asteroid belt. And so it's not really a target for mining, and unless you're in some fantastic visionary future where humans really have populated the solar system. But I personally think, and I really agree with Jeff Bezos on this, that it would be to our great benefit to move the heavy metals and minerals industries off the surface of the Earth, and to mine material from space where appropriate and where possible. Now, as you say, Planetary Resources didn't make a go of it in the end. And what an amazing company that was, and run by a super genius, Chris Lewicki. But investors are not used to 30-year payoffs. They are used to seeing every quarter by quarter go up. And so we're just not there with Planetary Resources yet. We're not there with asteroid mining yet, but there's so much work on it going on right now. And the moon is going to be a major target. I feel optimistic about being able to get some key resources from near-Earth asteroids and from parts of the moon in the future, and do some preservation on this planet, which is the best planet we will ever have.
Thank you very much.
Thanks for your question.
Yeah, that was great. Sam, you have any questions?
I didn't have any questions. I just wanted to say thank you for such an engaging and interesting presentation. It was so fascinating. I didn't know much about planetary formation and the different theories that were being postulated for how these objects form. So it was really incredible. Thank you so much.
Oh, thanks a lot, Sam. I appreciate it. Yeah, I always try to like tread that line. Like I think that if people who are not scientists come to the talk, I don't want to condescend to them and not show data or not talk about specifics, but I try really hard to make them comprehensible, and I know I don't always make it. So it's nice to know when it works.
Yeah, that was brilliant. I love all the artwork that you have to illustrate all of these things. Is that something that you had kind of built in from the beginning, or as this mission got rolling, you said, oh, it would be nice if we had some nice pictures? How did that work?
It's both of those things. Part of it is, like I was saying, like the cover art for the proposals, and then realizing that it wasn't just the engineers who didn't have the mental film strip of the formation and melting of planetesimals and core formation, but the review panel didn't have that, right? So we needed to find a way to communicate to the reviewers what story we were trying to tell or discover about. And then we've continued, and in fact, very shortly, we're going to have 2 new videos from Peter Rubin about possible ways that Psyche could look. And he does it because he's an artist, a Hollywood artist who works on movies. We're zooming over the surface of Psyche with the spacecraft and the shadows going here, and there's lens flare, and you see the ion thrusters. And so those are going to be released over the coming months. I'm very excited about it.
Yeah, that's great. I love it. I feel like space science is just ideal for that kind of like really engaging and compelling visualization. All science, so much of science is very interesting, but space science, I think especially, is really just perfect for that kind of engagement.
Yeah, I agree.
We have a question here from the YouTube chat. Is there or has there been an ice asteroid mission? An ice asteroid.
Oh yeah, well, I mean, an ice asteroid is really a comet. once it gets close enough to the sun to have a tail, and so that Rosetta was the unbelievable mission from European Space Agency that sent, if you remember, that little lander down, and it was lost, and then later they found it, and it bounced under a ledge. And the comet, very much smaller than Psyche, had this bizarre shape, and then they saw like ice falling down. It looked like it was snowing on the comet. I mean, that is a mind-blowing mission. Everything about it, every image, every incredibly brave thing that they tried to do, high-risk things, and all that they learned about icy asteroids and the kinds of materials they're made of. So that's the one that springs immediately to mind. But you could also say New Horizons to Pluto is an icy asteroid mission in a way. Now they're looking at Kuiper Belt objects that are made of ice. So yes, absolutely, yes.
Yeah, that's great. I just have to ask, I hope you don't mind if I ask some more scientific technical questions. One of my favorite classes that I took in graduate school was Mike Drake and Jay Milosh taught a course called Terrestrial Planets.
I cannot imagine what a master course that must have been.
It was so fascinating, but I never completely understood how an impact could remove the rocky outer layers of one of these planetesimals, or of, I don't know, Mercury. So how exactly does that process work? I imagine you have an impactor coming in from one side. I can see you could vaporize or spall off material on that side, but can you remove all of it in one impact like that, or how does that work?
No, you can't do it, and we don't think you can do it in one impact. And so this is largely the work of Eric Asfog and Bill Bodke, another one of these guys in our field who kind of knows everything and has been a great guy. He's also on the mission, and he coined the phrase hit and run collision. And so if you have these, okay, so just think of, and weirdly, like, nobody did this work for a long time until Eric did it. But if you think about it just intuitively, one of those rare cases where that actually works with space physics, you have lots and lots of planetesimals all orbiting around the sun, and some of them are moving radially because they've gravitationally interacted. You're going to have misses, you're going to have direct hits, and you're going to have grazing impacts. You're going to have all of those kinds of impacts. And people had really only studied direct hits. But it turns out probably half of the impacts are going to be grazing impacts of some sort. And there's a large fraction of those grazing ones that will knock material off that won't reaccrete. But one is not enough. You're so right. So 4 to maybe 11 was what seems to be needed to knock all of the rock off, or as much as it would kind of match Psyche. But here's the thing. That's our favorite hypothesis for what Psyche might be. But Eric has run kind of a Monte Carlo suite of many, many solar system creation scenarios. And in most of them, nothing like Psyche is created, because 4 to 11 grazing, non-accreting impacts with no accreting impacts in between is very rare. And so every once in a while, you would get a solar system with one thing like Psyche, and every once in a while, 2. So that Psyche is satisfyingly rare. And there is only one in our solar system, so maybe that is the case.
Okay, that exactly answers the next question I was going to ask, which is, why don't we see more of these if this is this thing that happens?
Yeah, right. And this is where I have to insert my standard disclaimer, like the fine print. Like, we don't know what it is. It could be that everything I just said is wrong, and it's going to be something completely different. But it is of those asteroids in our solar system that we think could be made of metal, X-type asteroids or M-type, depending on what characterization system you like. There are only about maybe 9 that we think are probably made of metal. And the largest one besides Psyche is Cleopatra, which is, I believe, about 50 kilometers long. So Psyche's 230 kilometers, so much smaller, and also very thin and shaped like a dog bone. So if any of you have not looked at Cleopatra before, just Google it right now, spell it with a K, and write asteroid and see pictures of this thing. There's distant pictures of it, so we know its shape. So there's really nothing else like Psyche in our whole solar system.
Wow, okay, that is really interesting. Let's see, Heidi, do you have any questions? I want to make sure everyone. I could just keep asking questions. And asking questions on YouTube. I want to make sure that other people get a chance. Do you have a question, Heidi?
Can you tell us a little bit how 800 scientists work together and how? Sounds amazing.
It is pretty mind-blowing. So it's not just scientists, it's like engineers of every kind, budgeters, financial people, schedulers, graphic artists, everybody, and people at headquarters, people at Marshall Space Flight Center, people at all the centers around the world that are working with us. And it is not an easy answer how we all work together. And because it's one of these things where I have responsibility. Like, I literally signed my name to Congress that if I knew a reason that this mission absolutely could not work, that I would halt it. And so I do have responsibility to have some sense of really what's going on. But these different organizations, we're bound together by contracts, but we don't literally report to each other. So it's responsibility without authority. And a lot of us have this all the time in our lives. And it'll be very familiar if you never thought about it before. Oh yes, I have responsibility for that, but no authority, right? Okay. And so it relies on communications and teamwork and just trying to stay in touch and creating a culture. The thing that is most miraculous about this whole thing to me is that we're creating an object that is so complicated that no single person understands how it works. And if you haven't thought about that before, think about it for a second. No single person on the team understands how the whole thing works, but it's got to work together flawlessly in space for decades. And JPL and other space agencies have done this before multiple times. And that is the miracle of systems engineering, all the ways that people have figured out to write requirements and make agreements when things need to change, and to look at liens and threats and risks. There are all these systems that systems engineers have put together. So I think of system engineering as one of the major evolutionary steps in humankind, that we can now create things that are this complicated that no one person understands them.
Wow, this is really amazing.
It's been a lot to learn about. I've enjoyed it so much. Yeah.
Actually, another question. So at one of your early slides, you said there's a question, there's a story that you didn't have the time to tell.
Yeah, do I have time, Brian? Do I have time to tell the asteroid story?
Oh yeah, I'll just let folks know that it's just now 8:30. You're of course welcome to stick around. Usually when we do this in person, usually this makes more sense to have this break at 8:30, let people leave the room. But of course here, yeah. Please tell the story.
Yeah, sure. Right. So in the 18th century, two people, or actually more, but mainly two people, created a kind of a little equation that ended up being called the Bode's law, the Titius-Bode law, that actually predicted the space between the planets quite accurately: Mercury, Venus, Earth, Mars, and then something, and then Jupiter, and so on. But it predicted there should be a planet between Mars and Jupiter. And in a way, this is just such a ridiculous thing, because even then people understood that given any spacing of objects, you can create polynomial that gives you those spacings. Like, that's not actually an amazing God-given miracle that they could find this equation. But it was interesting that they did find one that did all the planets, except it predicted this missing planet. And so astronomers all over Europe got together and decided they were going to find the missing planet. And they were led by an astronomer in Germany named Franz Xaver von Zach. And he put all these people together. And they ended up getting a nickname, which was Die Himmelspolizei. Their job, the celestial police, is the way that it gets translated from German. And really what they were saying is, we are going to set the heavens straight. We're going to make order in the heavens by finding this missing planet. And so they set off trying to find the planet, and with the best telescopes that they had. And of course, the first thing they found was Ceres, which, am I right, it was 1806, I think. Maybe I'm wrong about this, but I think that's the right date. And that's the biggest asteroid. And then they found a couple more, and eventually they found Psyche in 1852. And eventually they realized there was no planet there. There were just these little things called asteroids, which really meant stars, and no planet at all. But they started that numbering system, which continues to today. We're still numbering our asteroids. And I think it was disappointing to Die Himmelspolizei when they finally realized that there was nothing to set straight in the heavens. So that's the story of the asteroid discoveries, which I love so much.
This is so cool. Thank you.
Well, let's see. Anyone else in the room have a question? I have to ask a question. My wife and I have recently gotten into the show, so I want to see if you've seen it. Have you seen The Expanse?
So I have started watching it, but I haven't gotten that far into it yet. But everyone tells me that I must watch it, that this is the thing. Yeah. Yeah. Do you recommend?
I do, yeah. So it had been recommended to me. I watched the first episode or two and I thought, oh, this is really complicated. I don't know if I'm going to follow it all. But then I sat down recently and started watching it again and just sort of forced myself to watch the first 5 or 6 episodes. And yeah, it's really good. Now I got my wife stuck on it too, so we watch that every night. But it's all living in the asteroid belt and on Ceres and Eros.
That is awesome. I would recommend along with that Neil Stephenson's book, 7 Eves. It's a palindrome, by the way, 7 Eves. Fantastic book, I thought, just really mind expanding in so many ways.
Yeah, that's great. Okay. I don't have any other questions here on the YouTube channel, unless anyone in the room has any other questions. Justin recommends 7 Eves as well.
Yeah, Justin, isn't that amazing? Yeah.
Well, thanks so much for joining us. This was excellent. I really am excited about this mission.
Thank you for the invitation. I enjoyed it very much. I really enjoyed meeting all of you right here in the room, and thanks to people who came online. That's great.
And let me get you to stick around for just a minute. So folks, thanks for joining us again. And the next one of these is going to take place on the first Friday of April. And I was corrected. I meant to say April 2nd. April 2nd is the next one. We're going to have Dr. Ami Choi from Ohio State University talk about some astronomy research that she's doing. I think that'll be really interesting. Our third Thursday virtual planetarium show, that'll be on March 18th. And I've put the link in the YouTube chat if you want to join us for that. We ask that you register. And with that,